Okay. Dear colleagues, it's my great pleasure to introduce our today's guest, Yaroslav Tserkovnyak. He is originally from Ukraine, from Vishnevo, Kyiv Oblast. He graduated from Kyiv Mathematical and Physical Lyceum in 1996 and moved in 1997 to Vancouver to the University of British Columbia, where he obtained bachelor degree. And shortly after, he moved to Harvard and studied there and earned PhD degree under supervision of known physicist Bertrand Halperin, who actually was the student of this year's Nobel laureate John Hopfield. So Yaroslav, to some extent, then successor of our of this year's Nobel laureate. After finishing PhD, he stayed in Harvard for about 3 years and moved to University of California, Los Angeles, where he started leading the research group since 2006. He is leading the theory group, condensed matter theory group. He was distinguished by a number of fellowships and awards, for example, von Humboldt Foundation, Simons Foundation, NSF, etc. His research interests are devoted to quantum transport and non-equilibrium phenomena in low-dimensional quantum systems, with a special focus on spin topology. Today, he will tell us about using atomic defects to sense and harvest quantumness. So please, Professor Tserkovnyak, the floor is yours.
Thank you, Andrei. It's my pleasure to give this seminar. My first time in Kharkiv, unfortunately remotely this time. I have never been to Kharkiv. I'm looking forward to give this another talk in person after the war. It's one of the first cities I would like to visit when the war is over. The talk is about using atomic defects to sense and harvest quantumness. I will start with a general introduction, explaining what I mean by this. I will build things up from basic level, starting with a single defect, going to multiple defects. The main thrust is going to be towards combining quantum defects, highly coherent, scalable quantum defects, on the one hand, with non-equilibrium devices. Again, some kind of scalable devices on the other hand. So in some sense, combining quantum technologies with conventional technologies, using quantum to sense conventional materials as well as exotic materials and devices, and then ultimately turning things around and using scalable electronics to control quantum dynamics in ways which are maybe different, hopefully different from the traditional things that you might have heard about before. I will be talking on behalf of my group members, Eric and Shane are postdocs working on the topics. Vince is a student. Previously, my former group members have contributed to some of the earlier work in this vein. Prame, Benedetta, G, and Susie. They have faculty positions of their own scattered around the world by now. And my experimental collaborators, Chunghui, Tuno, and Amir. I'll mention some of the experiments by these people. I'm not going to go too deeply into those experiments today. Please feel free to interrupt me during the talk. I'm happy to follow your lead in terms of the dynamics. Feel free to stop me, and if you find something interesting that you want to focus on in the discussion, I'm happy to follow your lead. Okay, so high-level cartoon. Imagine you have a bunch of qubits, and we're going to start from 1 to 2, and then ultimately many, but today we'll talk mostly about 1 and 2, and then it will be kind of clear how things would scale up. We have a bunch of qubits. Suppose that these qubits are sufficiently on their own, sufficiently good qubits. So they have high coherence, but they're not interacting. So each of them has high coherence, and there is an ensemble of them. They're largely decoupled from everything else, and they're also decoupled from each other. We can drive them, we can manipulate them, and we can measure. Now, at that level, nothing interesting is happening before we connect, before we make them talk to each other somehow. Okay, so I will do that via a medium, via a common environment. Okay, normally you use that environment to mediate some kind of coherent interaction. Today I will focus on a more general setting in which environment results, in addition to coherent interaction, results in dissipative dynamics. In fact, I will focus on the regimes in which dissipative dynamics dominates. Okay, so we have some extended material. It could be a substrate. I will make it more specific later. Now let's just imagine this kind of in the cartoonish form. We have a substrate, a bunch of qubits placed over the substrate. And the substrate, for starters, it could be in equilibrium. Then I will drive it out of equilibrium. But let's first start with the most minimalist, bare bones setup. So the substrate is in equilibrium. Even in equilibrium, however, it generates some noise. Okay, that noise is due to thermal fluctuations, and at very low temperature, there are quantum fluctuations, which are also contributing to that noise. I will be mainly interested in the regime in which the quantum component of the noise is important. It's this quantum component of the noise that ultimately I will harvest for something useful. But first, we need to understand what we even mean by that quantum component of the noise. Okay, so that's the first goal. So in some near field noise that depends on all of the various details ultimately of this material. I'm sorry, the sound is really bad. Sir, I could not hear.
Yeah, we'll fix it. Sorry for that.
Okay, I continue.
Yes, please.
Okay. Okay, so the material emits some equilibrium noise, and that equilibrium noise perhaps can induce some interesting dynamics. So you could initialize the qubits, subject them to this noise, wait for some time, essentially via the qubit dynamics, integrate that noise in some form, and then perform the measurement. Okay, that's sort of a typical sensing modality. So through that measurement, then you try to learn something about. Do you also see this, hearts? There's something funny on,
yeah, very nice
on my screen. Okay, I don't know what that is. That's strange. Okay, so those are the two questions I'm pursuing. Okay, first, imprinting quantum correlations onto this array of qubits by natural dynamics, and then exploiting those correlations for sensing of the underlying material, as well as ultimately, that's more longer term of an objective, using that process to perhaps, for example, imprint some computational task, some quantum mechanical computational task onto this array of qubits. In other words, you put the qubits next to the material, do something to the material, imprint quantum correlations, and then my goodness, what? Do you also hear that strange noise?
Yes, trying to figure out who was speaking.
All right, I continue. All right, so let's start from the basics. Let's start with the single spin. This was Larissa. Somebody it said.
Yes, I switched her the microphone several times. Probably we need to ask her to leave our meeting.
All right.
External noise in our quantum meeting.
Yeah. So, in this talk, the point I'm going to try to make is that noise, usually we think of it with negative connotation, but for the purpose of this talk, noise is good. It's really going to do good things for us. We will exploit it for sensing and harvesting. It's going to be quantum noise that will be performing useful tasks, hopefully. So at the level of single spin, things are very simple. There's really not, there's just not enough complexity at the level of single spin for anything interesting to happen. But let's quickly remind ourselves what happens if you put a single spin weakly coupled, a single qubit weakly coupled to some environment. So without the environment, the spin undergoes Larmor precession at the frequency of the splitting, omega. Subject to the local noise, that Larmor precession will decohere. So it will dephase as well as relax. So if you start in a ground state, it can get excited. If you start in the so Hamiltonian, both. So the coherent dynamics is described by Hamiltonian. The decoherence is going to be described by Lindblad jump operators. Not going to go into introduction what this. I'll assume you have some knowledge of that. In fact, not much knowledge of that is needed for the purpose of this talk. So, for example, for the Hamiltonian of this form, the ensuing dynamics is Larmor precession around the z-axis. The raising lowering operators describe jumps between let's say the lowering operator is describing jump from the ground state to the excited state. The raising operator describes the jump from the excited state to the ground state. So this process is describe relaxation and excitation. The characteristic timescale for these jumps is known as T1 type. The dephasing that's described by the jump operator like Hamiltonian sigma z is characterizing the T2 time. Okay, so Larmor precession with occasional jumps between excited and ground state and dephasing. Nothing really that interesting, and because of the simplicity, both the Hamiltonian and the jumps could be expanded in terms of the Pauli matrices, and there's really not much else beyond what's shown on the slide that you can get. The only utility of such an environment from the point of view of qubit dynamics could be perhaps qubit initialization at low temperature. If the temperature of the environment is less than hb omega and there are no drives whatsoever, and you could imagine drives acting on the qubit or drives acting on the environment, there are none of those drives, then the only possible utility of such an environment could be to initialize the qubit in the ground state. Initialization is also important, of course, for quantum tasks, and then subsequently you're going to do something to that qubit. So that's what happens at the level of open single spin dynamics. Even at that level, however, the quantum mechanics is already lurking in this story, and that's something that you appreciate when you look at the so-called Einstein's relations between absorption and emission. So at the level still single qubit dynamics, the emission or the relaxation of qubit, which is associated with emission energy into the environment, it has two pieces, spontaneous and stimulated, while the absorption has only one piece. It's only stimulated. There's no spontaneous absorption. You can't absorb energy from vacuum. According to fluctuation dissipation relations in thermal environment, irrespective of the details of the environment, it could be bosonic, as sketched here, it could be fermionic. Any environment, as long as it's in equilibrium, has the following relationship between absorption and emission processes. The ratio between absorption and emission is given by the Boltzmann factor, h by omega, that's your qubit splitting temperature, which I want to write in this form as the ratio between Planck distribution and Planck distribution plus 1. So this Planck distribution here corresponds to absorption. Planck distribution plus 1 corresponds to stimulated plus spontaneous emission. So this plus 1 is the spontaneous emission. Whenever that plus 1 is adding significantly to the Planck constant, namely the Planck constant is of order 1 or less, the spontaneous emission is playing a role, and that is the regime in which the environment is starting to behave quantum mechanically. So from the point of view of the single qubit dynamics, whenever this plus 1 is significant, which corresponds to temperature being lower than h by omega, in a way the quantum mechanics is already operative. So that's the regime. That's the regime we want to be at. In the classical regime, there's there's a symmetry between absorption and emission, so that 1 corresponds to the classical limit. Otherwise, when the spontaneous emission is playing a role, we already have quantum dynamics. And I remember learning about this many years ago in my lyceum in Kiev, and somehow that really blew me away. And of course, there's always fun to mention connections to Einstein, even though Einstein was always throughout his life antagonistic to quantum mechanics. His contribution to quantum mechanics, even to quantum mechanics, is spectacular. Okay, so where do we stand? Let's summarize so far. So the relationship between absorption and emission is a purely thermodynamic one. It's always true, irrespective whether there are intricate quantum fluctuations in the environment or not. Nevertheless, even if the environment seems extremely boring, at very low temperature, even the boring environment somehow is already reflecting some quantumness. When temperature is less than the splitting of the qubit, even boring environments somehow already yields some quantum aspects. However, at the single qubit level, it's all pure thermodynamics, and that intricate quantum mechanics doesn't seem to be really contributing to any interesting dynamics. So the dilemma here is how come, on the one hand, at low temperature, some of the quantum mechanics is cropping up, and that's perceived by single qubit dynamics through the spontaneous emission. On the other hand, it doesn't really yield to any interesting quantum dynamics. Well, that is really because at the level of single qubit, it's just there's not enough complexity of the system, and this dilemma is going to be resolved by going to multiple qubits, and already 2 qubits turns out to be sufficient for interesting physics to start cropping up, and I'll explain what I mean by that. However, even for 2 qubits, as we'll see, the fluctuation dissipation relations are really constraining what can happen, and that escalates the problem escalates to scale to many qubit system. That's what driving systematic will be of fundamental interest to us. Okay, so we're going to go from 1 qubit to 2. Appreciate how fluctuation, kind of basic thermodynamics, is still limiting us, and that's where the non-equilibrium phenomena will start playing a key role. And I'll give you 2 examples of the kinds of things we're thinking out for equilibrium at the end of the talk. Okay, so just to summarize, characterizing single spin dynamics is still useful to herald quantum regime of low temperature. Once we reach that limit experimentally, then we're going to go to multi-spin regime, multi-spin scenario for both for harvesting and sensing. And harvesting and sensing will go, of course, hand in hand. All right. So having said that, it's easy to appreciate that there is definitely plenty of quantum mechanics around us. Even, look around the rooms you're sitting in. There are certainly plenty of metals around. Even at room temperature, they are degenerate Fermi gases, highly, with strong quantum fluctuations. There are magnets everywhere around, which certainly are not allowed by classical physics. So there is microscopically quantum mechanics playing out, and even all the colors we see around, that all comes down to to quantum mechanics at atomic scale. So plenty of quantum mechanics around us, but it's not manifested in macroscopic phenomena the way we learn about classical mechanics, thermodynamics, the way we teach students in college. This quantum mechanics is really not manifested in quantum correlations, quantum entanglement. So it's hidden. It's there, but it's hidden, and it's what I'm trying to talk. I'm trying to sort of tap into quantum mechanics that is omnipresent, but so here's the question: Can some kind of designing a little microscopic probes, can those be sensitive to quantumness? So quantumness is hidden from macroscopic phenomena. So naturally, you wanna go down to microscopic scale to start sensing and harvesting that quantum mechanics. But the objects that will yield us quantum mechanics are going to be this semi-classical reservoirs around us. So that's how I visualize combining quantum degrees of freedom with sort of initially featureless correlations in the environment, but I'm going to look microscopically at those correlations, and then finally I'm going to see quantumness, and I'm going to harvest that quantumness in some scalable fashion. Okay, so as I've said, one elementary spin is not enough, even though it will herald the onset of quantumness, but then we'll have to scale up. And moreover, even when we do that, there will be some interesting transient quantum dynamics, but to get a more robust and steady state quantum sort of induced quantum states, we're going to go to non-equilibrium, and that will be rooted in some fundamental relations, irrespective of microscopic details. Okay, and then I want to ask about what sort of non-equilibrium knobs that will be might be useful later, such as currents, thermal gradients, microwave drives. So all those sort of conventional classical knobs will eventually be utilized by us to prepare quantum states. Okay, so the knobs will control macroscopic objects, but then our little color center demons will be integrating that noise and evolving in some complicated way. And again, you could imagine that can be used for sensing, as well as ultimately for some kind of quantum state preparation, maybe even from some tasks, some computational tasks. Okay, so then the question is, well, how much of a resource can a passive but macroscopically control materials, devices, heterostructures present for quantum information science and technologies? That's what this talk is about. So I'm going to treat my environment as being passive, other than some gentle macroscopic controls, like sending a current or applying a thermal gradient to that environment. I'm not going to be performing like any intricate pulsing sequences or any intricate manipulations. I want to replace any intricate kind of microwave manipulations, optical manipulations, with gentle sort of more like electronic control of the environment. Okay. Let's, with all that in mind, let's get started with, defining the main workhorse of the story. So the main workhorse is going to be a color center, which will play a role of a qubit that will be optimal for my goals. Why so? Because an individual color center, let me exemplify a color center in this talk by NV, nitrogen vacancy, defect in otherwise a pristine diamond. So that's probably by far the most commonly used color center nowadays for quantum, mostly for quantum sensing. But now I want to sort of think of this color center as qubits in more general sense. By themselves, they're pristine objects, highly coherent even at room temperature, very versatile. You could plant many of them. By now, many ways to implant them, to place them, to combine them with condensed matter systems. Again, you could place them in some diamond rod. You could drop that rod on a substrate. You could put it on a cantilever in some kind of scanning modality. Sophisticated microscopies that people have developed to initialize and measure such color centers. So they're really perfect objects for my purposes. However, on their own, they're pristine qubits, but really they don't do much on their own other than integrating noise in a T1, T2 fashion, in a sort of ESR fashion. So they've been used as a kind of ESR sensors up to now, primarily. Which again, for me, is a good place to start because I want them to talk to each other via the environment. So on their own, they're pristine, and then when I put them next to some physical environment, it's through that environment that I want them to start interacting, sensing that environment, and harvesting quantum fluctuations from that environment. Okay.
Sorry.
Yeah.
Andrei is asking, are you talking about 2 qubits, or you are thinking of more and put in environment between, so to say, pairs, or 3 talking to each other?
Right. So I'm starting with 1. So I'm going to start with 1 and then build up from there. So with 1 qubit, there's not much we can do, as I've explained. But we're still going to start with 1 and see, and I'm going to quickly remind you what people have accomplished with 1 such NV center for sensing. Then we're going to go to multiple. So with 1, you could do some sensing, but you cannot induce interesting quantum dynamics because there's really not much is happening with 1 qubit. Then we're going to go to the main interest is going to go to multiple. And making them talk through the environment, through the dissipative environment. They will talk through collective dissipative fluctuations in the environment.
So the question was, is it pairwise always, or more complex than if you build more and more? Or they talk like only between pairs?
Oh, they will, yeah. So the coupling to the environment is going to be weak.
Okay.
All the interesting things, yeah. So right. So in that sense, coupling to the environment is, in a sense, is going to be very simple. And then in that weak coupling regime, we're gonna develop the appropriate Lindblad formalism, which yields to pairwise interaction. Yeah, the leading order, the leading order interaction is of course just pairwise. So yeah, each pair will talk to each other. But of course, that happens simultaneously. So there's the collective, even through pairwise interaction, of course, collective effects develop.
Thank you.
But let me get a little bit further, and then you can maybe ask more specific questions about it. So a quick summary: as a qubit, an NV center is described by the leading order. The main piece of the Hamiltonian looks like this: as a Zeeman coupling, as some anisotropy along the axis of the NV impurity. So the z-axis is along the line connecting a nitrogen and a nearby vacancy. S is a spin 1 operator. So there are 3 levels: 0, +1, and -1 projections of spins on the z-axis. So you could pick any pair, let's say -1, 0 pair, and think of it as a qubit. Might as well think of this as a three-level system. It really makes little difference. Okay, so if we're focusing on this transition, let's call it a minus qubit. So there's some rates, relaxation rates. We're going to refer them as, let's say, a gamma minus. And then when we switch to this transition, then okay, well, let's designate it as a +1. The other details of how you manipulate optically this NV are not going to be so important for us. Let me just outline the essentials. So this is a more complete picture of level structure of the NV. The interesting part for us is here at the bottom. So that's where the qubit lives. These are the three levels described by this Hamiltonian. And what you should know that this this anisotropy is somewhere in the ballpark of 2.8 gigahertz, let's say 3 gigahertz. So it's microwave frequency range. So if you live here, you will manipulate qubit dynamics with microwave pulses. And if you want to couple to the environment in this energy subspace, again, it's gigahertz frequency scales that will be relevant for us. Okay. Moreover, if you want to induce quantum noise, well, the gigahertz sets the temp. If you want to use environment without any tricks, just passive environment equilibrium, then you have to cool down to sub-Kelvin temperatures for thermal fluctuations to start acquiring some quantum character at this frequency range. The rest of this picture here is just used for initialization and the readout. So you initialize a qubit in a MS equals 0 state by driving it with a green laser. That's a sort of a standard color center details. You could just, you could relax re-emitting redshifted photoluminescence, or there is a side trip that you could make through some non-radiative processes, which the side trip distinguishes between MS equals plus or minus 1 versus MS equals 0. The bottom line is if you drive the system with a green laser, you will initialize a qubit in the state, then let it evolve within this three-level manifold. That's what we're going to be doing now, and we're subjected to some environments. We're going to evolve in this manifold. After some time, then we again shine a green laser on it, which effectively projectively measures whether the qubit is in a MS equals 0 state or in one of these excited states. From the point of view of photoluminescence, the MS equals 0 state looks bright. MS equals plus or minus state looks dark. So that's all you need to know about NV, is that it's a three-level system that can be initialized in the ground state, and then we can manipulate it as we wish with pulses or the environment, and then you could projectively read out it by measuring probability to remain in a MS equals 0 state. Okay, the NV impurity looks red because this re-emitted photoluminescence is redshifted. So a diamond full of these impurities, will look like this. Which, well, this is a picture of a very expensive diamond. It's a specific stone that's, I think, the largest red diamond in the world. Okay. So far, already this modality has been exploited, with tremendous success in various sensing experiments. This is not so much about any interesting quantum dynamics. It's just an ESR, NMR type of sensing when you're using that block type dynamics, measuring either Larmor frequency or T1 or T2 relaxation times. You learn something about the environment. If you measure Larmor frequency, you learn basically you detect stray fields. If you measure T1, T2 times, you learn something about, for T1 times, you learn something about gigahertz noise coming from the environment. If you measure T2, you're going to learn something about megahertz, typically low frequency megahertz noise of the environment. This is just a quick rundown on a few things I was involved in this vein. This 2017 paper, that was actually my entry point into this business. I've been thinking about this problem since about that time. In this work, a single NV center was used to sense noise produced by yttrium iron garnet. It's a very famous insulating magnet. In fact, what I hear from my microwave colleagues, the best single crystal samples, or some of the best, maybe the best in the world, come from Lviv. So there's a company that makes YIG in Lviv. I don't think this one is from Lviv. This is the thin film, like 20 nanometer thin film of YIG. There's a single NV above it, and you sense noise from YIG. So if you put a single NV close to YIG, the natural magnetic fluctuations at room temperature produce a huge amount of noise from the point of view of NV that overwhelms NV dynamics compared to its intrinsic environment. Compared to the noise emitted by YIG, the intrinsic noise in the crystalline diamond environment of NV is completely negligible. So in that sense, we're going to think of NV as an absolutely pristine qubit, because for all our purposes, the moment we place NV close to some magnetic environment, that environment will dominate its dissipative properties. Everything else could be neglected. This is an example of this work is an example of a single NV measuring chemical potential of magnons driven out of equilibrium. In equilibrium, magnons have a zero chemical potential, like black body radiation. If you drive YIG out of equilibrium, and you could do it in many different ways nowadays, the traditional way is just some microwave dynamics, driving Kittel mode. More modern approaches using a spin Hall effect or spin Zebek effect to thermally or thermoelectrically pump YIG by subjecting it to electronic or thermal spin transfer torque. Whichever way you drive YIG, now you could perturb magnons and shift the chemical potential away from zero. And the main achievement in this experiment was sort of direct measurement of that chemical potential with YIG through the change in the noise emitted by YIG. So changing chemical potential of magnons shifts the populations of magnons, so that translates into different noise that you detect with NV. And by looking at how the relaxation, T1 relaxation of NV changes as a function of various drives, you could backtrack the chemical potential and relate that chemical potential either to your Kittel mode drive or spin Hall perturbation or spin Zebek drive. Then we went further and said, let's more broadly look at consider single NV spin as a non-intrusive sensor that can look at the transport properties of magnons. So here, essentially, we're looking at a distribution function, out of equilibrium distribution function of single magnons. In this experiment, we're looking essentially at two magnon processes, so conductivity, diffusion coefficient, things of that sort, and it's a non-invasive probe. Again, for the first time, non-invasively, one was able to detect the transport property of various magnetic insulators. In this experiment, it was hematite, antiferromagnetic insulator, as well as YIG. Any collinear magnetically ordered ferro-antiferro system is suitable for this kind of measurement. And finally, I was not involved in this experiment, but this experiment was based on a theoretical proposal that we made, that the NVs, not only they can measure chemical potential, transport properties, but they could also detect spatial textures through the Goldstone mode that those spatial textures imprint on the material. So this is a picture of a synthetic antiferromagnet with a bunch of domain walls. Those domain walls are invisible to the conventional magnetometry. Conventional magnetometry measures strafe field. These antiferromagnetic domain walls do not produce enough strafe field to be measured, but the Goldstone mode, the vibrational modes of these domain walls produce enough noise that you could measure these domain walls in the contrast of the NV photoluminescence. So these are the kind of examples that that demonstrate the versatility already of a single NV in the kind of ESR, NMR modality, not so suitable for imprinting any interest in quantum dynamics of NV. In fact, these are all room temperature experiments. Essentially, you're measuring classical noise with a quantum sensor. Okay, just like NMR, ESR, you know, those are kind of classical probes, but with quantum objects. Okay, but what's important for us is that it illustrates that NVs can be coupled strongly to a range of magnetic materials. You don't have to be married to magnetic materials. You could consider also, you know, we're looking at superconductors and other interesting systems. Even ordinary metals could yield something interesting. But in this talk, I will focus on magnetic materials. So we have strong coupling in the sense that you place NV close to magnetic material. The natural noise of that magnetic material completely dominates NV dynamics. Okay. So, but we want to go quantum. We want to go quantum, and for that we need to go to low temperatures, and you know, so we need to get to the regime in which spontaneous emission is also contributing to the dynamics. In the previous slide, those experiments were in the classical regime. So KBT was room temperature, h bar omega is sub-Kelvin, gigahertz, few gigahertz. That is sub-Kelvin, very low low energy scale. So we want to cool down. Okay, so we want to cool down, and of course, as you cool down, the noise, the total noise, as it becomes more quantum mechanical, also the overall level of noise will go down. So eventually, that noise might be negligible compared to the noise from the environment, from the natural environment of the NV. We don't want to be in that situation. So we want to be in the situation that we're cooling down, the noise is becoming more quantum mechanical, but the NV is still dominated by the noise coming from the environment rather than its intrinsic noise. Okay, so we want to characterize this induced decoherence onto a single spin as we're cooling down. We want to maintain the sizable effect even in the quantum regime when temperature becomes comparable and lower than h bar omega. Finally, once we get to this low temperature quantum regime, we want to go to coupled two-spin dynamics, and we want to see the quantum noise generating some entanglement between multiple color centers. So we're going to start with two. Okay, we're gonna now how we're gonna manifest that induced quantum dynamics. We will manifest it through the onset of some Dicke type superradiance, subradiance. Basically, those are the most immediate consequences of collective NV dynamics that indicate some induced correlation. And remarkably, even at the level of just two spins, already some kind of both superradiant and subradiant features, as I will explain, are starting to crop up. So in essence, the prediction, and this is so far this is a theoretical prediction. I'm discussing this with experimental colleagues. There are many challenges. It's very challenging to get to this situation, but people are working hard. At this point, it's just the prediction. But the prediction is that once these first three requirements are fulfilled, the rich quantum multi-qubit dynamics would be assured, assuming now the spacing of the NVs is compatible with the correlation length of the material. So it's a correlation length that is associated with the fluctuations in the material that produce the noise. So the noise needs to be correlated spatially. Of course, if the noise is quantum but completely uncorrelated, then NVs will not pick up any correlated dynamics. Now it's in this length scales that the underlying physics is kicking in, and that's kind of a resolution of this dilemma that at the level of single spin, everything is governed by thermodynamics irrespective of any interesting quantum correlations in the material. The moment you start looking at two or more spins and interesting quantum dynamics along these lines is cropping up, now the physics of the correlation lens and in conjunction with the spectral properties is now starting to reflect the underlying physics. Now, some boring material governed by Fleck-Tonge dissipation relations is not going to be enough. We're gonna need to look for interesting materials with sufficiently long correlation lengths, which reflect the intricate quantum dynamics at our relevant energy scales. Okay, so that's what the interesting scalable quantum dynamics of the NVs happen in conjunction with some interesting correlated physics in our substrate, and now somehow things are starting to make much more sense in terms of both sensing and harvesting non-trivial quantum dynamics. We've developed the formalism that is needed was developed a couple of years ago in this paper. In essence, let me just summarize the essential ingredients. If you look at the level of just the two spins, sigma 1 and sigma 2. Now, in addition to T1, T2 type of decoherence, so we have some local decoherence. In addition to that, we have now non-local decoherence. Remember, I said I will be focusing on dissipative dynamics in this talk. So the local decoherence at the level of master equation, rho is the density matrix. Looks like this. Sigma I are the local spin operators. A, the little a here is local relaxation. Oops. The A tilde is the local excitation. You have now the capital A and A tilde. Capital A is the non-local relaxation. Tilde A is non-local excitation. At the level of the master equation, they yield terms like this. So it's processes of this form. Now combining the dynamics of spin 1 and spin 2 in this fashion that I will refer to as non-local relaxation, and in a similar fashion, non-local excitation. So we developed a systematic field-theoretic formalism for such dynamics, basically relating these terms that go into the master equation to the correlation functions of the material. And now one has to be careful to distinguish between coherent dynamics imprinted on this multi-qubit system, dissipative dynamics, as well as one needs to be cognizant of various thermodynamic constraints. The second law of thermodynamics we explicitly invoke in the end of the day, which, by the way, dictates some relationship between the capital A and little a. According to second law, we can show that capital A, the non-local processes, cannot exceed the local processes. So then we have Fleck-Tonge dissipation relations on Zagor reciprocities. All those things are playing a role in connecting the intrinsic dynamics of the material to the kind of induced quantum dynamics of the qubits. So that it's all in there. It's important to be constrained by all this thermodynamics one, to get kind of non-pathological master equation. So if all the thermodynamic constraints are properly respected, the master equation is non-pathological. Everything works out, without any surprises. Moreover, you need to be cognizant of these constraints to appreciate that there's not such thing as a free lunch. Having properly invoked all these thermodynamic constraints, we will see that some interesting transient dynamics can be induced onto an ensemble of color centers, but nothing interesting happens in the steady state. For interesting things to happen in the steady state, we'll have to go out of equilibrium. We'll have to start lifting some of these thermodynamic constraints. So that's what I'm going to do. That's what I'm going to do later. Now, I'm not sure about the time. So can I still talk for another few minutes, or should I kind of start wrapping up? Maybe just summarize. Andrei, what do you suggest?
I suggest still you have enough time. So we are suggesting audience to ask questions during the talk. So I think about 20 minutes. What do you think?
All right. So let me so now this stage is set. Now I'm gonna summarize some of our most recent results, and then maybe we can discuss. You can ask questions. So at the level of 2 spin dynamics as just described based on the paper that I've advertised on the previous slide. Here's an example of something interesting already happening. If now only transiently some interesting quantum correlations develop. So, for example, if we start in some unentangled state, so the density matrix is given by a pure state, like up-down, subject to the environment now with some mixture of local and non-local dissipation, so still rather generic. Then we can reduce the 4x4 density matrix equation down to a simple harmonic oscillator equation that can be in a underdamped, overdamped, or critical regime, just using terminology of a simple harmonic oscillator. Now, turns out, depending on the relationship between this is detuning between the two spins. A is the local relaxation, capital A is the non-local relaxation. Depending on the relationship between these parameters, we can have some transient entanglement that this initial state will produce. Eventually, however, this initial state will give it long enough next to this passive environment. It will, of course, relax to a Gibbs state, to a boring, unentangled Gibbs state. But transiently, there's entanglement that builds up. Depending on whether this equation is in the undamped, underdamped, or overdamped regime, the entanglement can oscillate with time, or let's in the underdamped situation, and the overdamped situation, there's a peak and then it relaxes. In some extreme idealized regime in which there is no detuning and the non-local relaxation approaches local relaxation, it cannot exceed because of basic thermodynamics. So the upper bound for non-local relaxation is given by the local relaxation. You get this red curve along which this initial state results in an equal mixture of the unentangled ground state at long times plus a singlet, so 50% unentangled ground state, 50% belt state. But realistically, maybe on very long time scales, it will still relax and it will come down. So something interesting is already cropping up, but only in some transient fashion. So we have some spike of the concurrence. This concurrence characterizes entanglement between the two spins. Concurrence 0 means no entanglement. Concurrence 1, maximally entangled. So such a state, a mixture of unentangled and a belt state, has concurrence of 50.
I apologize. My question: what is C capital in terms of X?
Right. There's some expression. Well, that's okay. So X is just one component of the density matrix. There are also other components of the density matrix that you have to express in terms of X. So concurrence is expressed in terms of the full density matrix. And then the point is that this little X actually parametrizes the full density matrix. And then there is some lengthy expression for concurrence in terms of X for this specific state. Which, okay, I don't remember what that expression is, but yeah, we have that expression in the supplementary material of the paper. The statement here is that this X parameterizes the entire density matrix. So once you know the entire density matrix, you could quantify entanglement by whichever measure of choice, which for us is a concurrence. Then, if you start in a different initial state, so up-down is a kind of a mixture of excited and relaxed single spin state. Up is the fully relaxed. If you start in down, fully excited, there will be the concurrence will stay 0, but there's actually a little bit of a super radiant feature that develops in the photoluminescence. I'm not getting into the details, but it's just amusing to remark that even at the level of two spin dynamics, depending on the initial state, you could either ensue some quantum dynamics or kind of imprint a little bit of sort of onset of superradiance. If you go to 5, 10, 100 spins, then you're going to see very strong superradiance in this treatment. Okay, so it's already a little bit of something interesting is cropping up, but still nothing that spectacular. One thing that we don't, it seems a little disappointing is that whatever the initial state, the steady state is generically Gibbs state, corresponding to the original unperturbed Hamiltonian. So this dynamics.
Could I ask a question, please?
Yes. Go ahead.
On the previous slide, you have this the graph of the concurrence, and is it exponential decay? It's just the decay too strong not to be seen, but was otherwise you could have something which is known as entanglement sudden death, no?
So it is no, it's all exponentially decaying. Yeah.
I see.
Yeah.
Okay.
Yeah.
Well, thank you very much.
Now, what we want, however, we want to get. Let's suppose we want to get some interesting state in the steady state. Okay, so that will not happen. That will not happen with this kind of passive dynamic subjected to a natural equilibrium noise. And you could prove it on general ground, irrespective of how complicated the intrinsic quantum dynamics is in the environment, as long as the environment is in equilibrium. We're back to some kind of Einstein type of relations between emission and absorption, and even for complex multi-qubit dynamics, interesting transient behavior. In the steady state, we will always relax to some boring Gibbs state governed by the unperturbed Hamiltonian. So to overcome this issue, we either need to cross over to some strong coupling regime that is beyond this Lindblad formalism, or maybe drive substrate out of equilibrium, which is the route we will pursue. So we'll still stay in this weak coupling regime. That will allow us to develop systematically sort of a scalable formalism. So from the formalism point of view, that is attractive. And it turns out the moment we go out of equilibrium in the environment and lift some of the thermodynamic constraints, now the game opens up and we can start generating interesting quantum entangled steady state. So that's where we're heading. Yet another strategy could be based on some intricate pulsing, coherent manipulations in conjunction with thermal noise from the environment. We will not be pursuing that route here. Okay, so I have maybe just 3 more slides, and here I just want to kind of, without getting into the details, just summarize the main physical idea. So the main physical idea here is the following. So imagine you have, again, 2 qubits and ultimately will scale to many in the environment, but now the environment is out of equilibrium. Suppose that means that the local noise is described by some one temperature that is different from the temperature of the environment. Yeah, because there's some net temperature of the environment. So as of equilibrium, the local noise is parameterized differently from, let's say, the natural noise of the environment. So there's some effective temperature of the environment, some effective temperature of the local noise, but yet different temperature of the non-local noise. So now there is no sense of a global temperature. If there is one global temperature of the environment, that global temperature is what is imprinting a Gibbs ensemble onto your color centers. If the system is out of equilibrium, all these effective temperatures are going to be different. In particular, if I have different effective temperature for local noise and non-local noise, in some sense, we have sort of like a thermal bias between local quantum dynamics, non-local quantum dynamics, which can now induce some non-trivial steady state. And the rationale, the kind of underlying logic that we're pursuing here is that.
Excuse me.
Yep.
May I ask a question? Do you have? Could you realize negative local temperature?
Yes.
Okay.
Yeah. Thank you.
But no.
Okay. Yeah. So we can, and before we go to negative, we can go to very low temperature. So now remember I said it was important that the temperature of the environment is sufficiently low. Now we can start with natural temperature that is maybe high, but make it effectively low by driving it out of equilibrium, right?
I'm sorry, can we realize such situation with laser or microwave radiation?
Yes. So, yes. So at this point, I just want to kind of give you a high-level cartoon, but then I can give you some examples, more specific examples. You know, I myself is a transport person. So if I think of non-equilibrium, you know, it's just the way my mind works. I'm trying to think of electrical currents, thermal gradients, some kind of device with some kind of electronic transport. But microwave drives and optic drives as well are relevant. But I want to emphasize those are the drives for the environment. Okay, so I'm driving the environment, and then by shaping the environment, you know, the qubits respond. But now you can drive the environment in principle in all of those ways, electrically with microwaves, maybe optically as well. I mean, for sure. Okay, and then the idea is, you know, we can now manipulate some local temperature. We can go to, you know, first again, one has to show that you could change local temperature significantly from the ambient temperature. Ultimately, maybe even flip the sign of temperature in the extreme case. And our logic is we want to. The reason why you get the Gibbs state, you know, is this Einstein relation between absorption and emission, and this Einstein relation, it constrains both local and non-local processes by the same Boltzmann factors. And it's the detailed balance associated with these relations that results in a boring steady state, even though there is intricate transient dynamics. If you disturb this detailed balance, so now you have deep processes, local, non-local processes, for which absorption and emission would be related by different Boltzmann factors effectively. So local processes, let's say by one beta, the non-local by another beta. Now the intricate transient dynamics will not necessarily settle at long times in a boring steady state. That is the logic. So we're disrupting the detailed balance that is due to Einstein, and then we can now open up the game and get to something interesting. One example of that, and that's again just my cultural tendency. You know, I'm a transport person, spintronics person. Something that comes naturally to my mind is inducing non-equilibrium spin accumulation. So inducing a spin imbalance in the environment that basically looks like a spin chemical potential of you know, conjugate to spin density. You know, so the environment now, you know, if you have a spin density in the environment, total spin in the environment preserved along the z-axis, that conserved quantity can now be pumped. Okay, just like you know, just like any electronic system has a chemical potential associated with charge, which is a conserved quantity. A conserved spin, for example, on the z direction, you know, can be pumped, and we can associate some conjugate chemical potential mu. So that's sort of the workhorse of spintronics. So like one example, just like driving electrical current through some magnetic multi-layer. Typically, you create imbalance between spin up and spin down electrons, and near the interfaces, it's this imbalance between spin up and spin down electrons out of equilibrium imbalance. So the imbalance between the spin chemical potential of different electronic species, that is the kind of spin accumulation that I'm utilizing here. Okay. Now, from the point of view of the environment, that spin accumulation is a kind of quasi-equilibrium property. So if you pump the environment, but we do it gently, the spin is conserved. So we can still treat the environment as a kind of quasi-equilibrium system described by this kind of generalized Gibbs ensemble. So that's the density matrix of the environment. It has temperature, and it has some chemical potential. But now imagine a situation in which our qubit does not respect this symmetry. So whichever symmetry in the environment that has U1 symmetry around the z-axis that allows us to introduce a spin accumulation, the spin of the NV does not respect that symmetry. And in practice, that is the case because NV, the color center couples, it's a magnetic dipole moment of the color center that couples to the spin fluctuations in the environment. And of course, dipolar interactions do not respect, I mean, they break all of the rotational symmetries in spin space. So the way the color center is coupling to the environment is not respecting the symmetry. Now the spin dynamics is scrambled in a way that disrupts detailed balance between local and non-local processes. And now we're able to induce interesting states even in the steady state. So here's a plot of now steady state concurrence. Now there's nothing needs to be fine-tuned. It's very generic as a function of local temperature and non-local temperature. Now they're different. If they're the same, then we have no concurrence. We're back to the keep state. The moment you have imbalance between local and non-local temperature, some interesting concurrence is induced. You still have, because the environment is a quasi-equilibrium, you still have some thermodynamic constraints on the environment. So you're not allowed to be in this region from some underlying thermodynamic constraints, some remnants of fluctuation dissipation relations, because the environment is a quasi-equilibrium. So ultimately, again, just to summarize, we can effectively cool down local dynamics. Maybe, well, it's difficult, but maybe even at room temperature, you could be able to cool down local dynamics to induce some interesting quantum effects, as well as, even more interestingly, cool down local dynamics relative to non-local dynamics. That disrupts detailed balance. That allows us to start sort of imprinting and generating interesting entangled quantum states in a scalable fashion in the steady state. Not going to go into detail here, but it's just to go to a more extreme regime. So that's the second example. The first example was kind of a gentle situation, which the environment is in quasi-equilibrium, but the environment to color center coupling disrespects that quasi-equilibrium of the environment and views the environment as being out of equilibrium. But still, it was sort of a gentle drive of the environment that was captured by some spin accumulation. A more violent situation that people have been discussing now in the context of some driven spintronic system is kind of engineering. It's not an analog of a black hole horizon. Okay, it's a big words, but it's some analog of black hole horizon, and as a result, analog of Hawking radiation associated with black hole horizon can be easily engineered by combining sort of like an equilibrium for a magnetic system to an inverted magnetic system. So imagine you have an ordinary magnet next to an inverted magnet. Of course, that inverted magnet is unstable. So magnetization, let's say, pointing in the wrong direction relative to applied field, it's unstable, but there are tools in spintronics that you could create this unstable state and then sort of weakly couple, again, with some spintronic manipulations, maintaining this basically turning this unstable state into sort of a steady state of the system. So it seems like energetically unstable, but it's pumped and you maintain the inverted state. The boundary between a ground state and inverted state of a magnet then acts as an analog of black hole horizon, producing purely quantum noise at low temperature. So at low temperature, each magnet by itself is not doing anything, but the interface between a good magnet and the inverted magnet is a source of magnon-antimagnon pairs, which we can now harvest in a systematic way. And now, because of this extreme circumstance and sort of very strong entanglement between magnon and antimagnon pairs, we are very generically and easily able to produce maximally entangled states between NVs in the steady state. That's kind of that is the basic idea. Let me skip some technical details here, just to show that again some picture from BBC. It's an artist cartoon of a black hole horizon that tears particle-antiparticle pairs apart. Antiparticle goes in, particle goes out as a Hawking radiation. That's exactly what we're doing. It's the pairing of particle-antiparticle or magnon-antimagnon pairs at that interface. But now nothing is disappearing. Both are coming out and are harvested by the color center. Okay, and again, this is concurrence as a function of some parameters of the model, and that's some sweet spot when you get maximal concurrence of one, maximal entangled state, but now in the steady state. So that completes my talk. obviously, in all of this, sort of sensing is kind of an underlying utility, but ultimately going beyond sensing, we want to be more ambitious and use this kind of sort of tailor our condensed matter solid state devices, driven solid state devices, and driven by any means, electrical, microwave, optical, subject to symmetries, as a spatial symmetries, as well as various thermodynamic relations. And it's a combination of those. For example, we used U1 symmetry in a material in spin space to allow it to manipulate spin accumulation. But then it's kind of sort of interplay of having symmetries, but also breaking those symmetries that allow us to tailor interesting quantum dynamics out of equilibrium. And these are the directions we're thinking about going forward with this with these ideas. Well, thank you very much for your attention. I want quite a little bit over time, but I'm happy to answer questions if you want to stay and ask questions. Thank you.
Thank you, Yaroslav, for wonderful talk. We have questions first from Mykola Bondarenko. Please.
I have a few questions, if I may ask them. Well, first, you began from the color impurities in crystals. So I wondered, well, this sort of activity is rather old. So we know that there are solid state lasers based on this mechanism. And what's your idea instead to build the decay super radiance also based on the impurities?
Oh, that's a great question. So all this like subradiance, super radiance, what we're trying to do indeed is what has been achieved in quantum optics long ago. Well, again, in some form. So for us, that is more of a demonstration that with solid state environment, we can induce some interesting collective quantum dynamics within color centers. Okay, so the focus here is that it's a solid state, it's a condensed matter setting. Our color centers are basically this kind of quantum optical objects that first we want to be able to integrate with our solid state system. So that has not been, well, that has been achieved at the level of single spin dynamics. You're just using them as single spin sensors. Now the next milestone will be showing that multi-spin dynamics can show some collective quantum behavior. Well, not even first semi-classical behavior like super radiance, which by itself, of course, would not be new, but that we view as probably the simplest indication of interesting things to come later, basically indicating strong non-local coupling with the environment. That brings us to the next step, in which we can now use environment, much more sophisticated environment than what's available in quantum optics. Quantum optics, the environment is just whatever, some cavities, some interconnects. Now our environment is rich, solid state, tunable, solid state system that we can take out of equilibrium in a very versatile fashion, which hopefully opens up opens us to new types of problems that are not accessible in quantum optics. So that is our rationale. So we first want to repeat some of the things which are known in quantum optics, and then utilize the power of condensed matter physics, solid state devices to take that to the next level.
Okay, if I got it right, first you're interested in sensing, and on the next stage maybe in super radiance, things like that.
Well, those things always go hand in hand, right? So at the level of single spin, the sensing has been already achieved and successful and all that. Now we want to see that two spins can show some interesting dynamics, which is different from a single spin.
Okay. Next question
so
is
some concept features of superradiance, subradiance as indicative of deviation from single spin dynamics. Now, Whether that immediately opens up new opportunities for sensing or not, it's unclear, but it will go hand in hand. Basically, sensing versus imprinting quantum dynamics will go hand in hand. That will indicate that we can imprint some interesting quantum dynamics. Then we can think of new modalities of sensing later. But for that, we need to probably scale, be able to scale up.
Next question. You showed us the big red diamond with some name, and I was wondering, usually diamonds are not actively used in this business, because unlike garnets and sapphires, the diamond is very rigid. It doesn't dissolve the impurities very easily, so it's not easy to control and dope the diamond.
No, these envy centers are in diamond. All those experiments have shown those color centers are color centers in a diamond.
Yaroslav, sorry to interrupt you. What if you stop sharing the screen, because we see black screen in front of us? If you stop, we'll see you.
Let me stop sharing. Okay, sorry. Okay.
Thank you.
Okay.
So all those color centers are in diamond. There are different types of diamonds. So it could be like a little diamond rod that you drop on your system. It could be a little piece of diamond on a cantilever, or it could be like a diamond film with many impurities. And then with confocal microscopy, you can.
Is it essential to make it uniform, like in lasers? You have to make the concentration of the impurities uniform in order for the lasers to perform well.
Right. So far, the experiments have shown that really just mostly at the level of single impurity.
Yeah. So you don't need it a lot. Yeah, I got it. Yeah.
Right now, next we want to go to multiple impurities, right? And now,
that's a different story. Yeah, right.
Now it all becomes issue of length scales.
Of course. Well,
can we space them so far apart that we can still control them with individual lasers? So then typically, to have full control, the spatial resolution will be diffraction limited. So it's like half a micron or so. So we're not that ambitious. We say, well, we cannot really, ultimately, we're going to compactify them maybe on a nanoscale. Okay, so we will not be able to individually resolve them, but we can still look at some interesting collective dynamics.
And then I was puzzled by the term harvesting the dynamics. What's this? How can possibly the dynamics be harvested? And what is harvesting? Is it producing and storing subsequently?
So one example is, let's say at the very end of my talk, you are setting up this spintronic system, you invert one ferromagnet, it's all kind of macroscopically manipulated, right? And then two NVs next to this interface between a regular and inverted ferromagnet, they are guided into the maximally entangled Bell state. So that interface, it's spewing as a flux of magnons, antimagnons. Now, two NVs next to the interface become maximally entangled. So that interface becomes a source of, and that's already kind of a distilled entanglement. It's a source of maximally entangled pairs, which you could use for.
So can you just say produce
quantum communication or whatever? So it's harvesting in that sense. So you are imprinting interesting quantum entangled, in some case extremely quantum entangled states. If it's a pair, well, a Bell pair is like the most interesting state you could get. But imagine now you have an ensemble of NVs at that sort of analog Hawking radiation interface. The kind of state you will reach, so we were thinking, what kind of state, how can we, it becomes a many-body problem. So we don't really know systematically how to address that problem. But we're thinking we have some ideas. And again, the ideas are rooted in this kind of notions of detailed balance and some hidden time reversal symmetry. So we're kind of still guided by this notion of detailed balance to try to figure out what kind of scalable quantum states we can get. But it's harvesting in that sense, imprinting quantum dynamics from the solid state environment, which is kind of hidden because macroscopically it's not manifested. Imprinting that onto ensemble of NVs and then using them for some tasks.
My last question is that you mentioned the situation when the strong coupling case, when you go beyond the Lindblad equation. Well, Can you say a bit more on that? How do you do that? How do you build this?
We do not. We avoid it because we don't have systematic formalism to kind of to go in that direction. So we avoid it. But one thing we can say is that for sure, if you go to strong coupling regime, you will get entanglement in the steady state, even in equilibrium. There's nothing that prevents you from doing that. Because in one hypothetical situation, those strongly coupled spins are basically part of your environment. So you could kind of fine-tune your strong coupling to be essentially for those spins to be kind of embedded in the environment. And of course, even in equilibrium, naturally within the environment, we do have entanglement between the different regions in the environment. So there's no doubt that in strong coupling regime, you will get some interesting entangled states, even in equilibrium. But we don't have a systematic formalism to address it. And moreover, we feel like it's more interesting to stay within the weak coupling regime because things are scaling up already in an interesting way, and and we have a theoretical handle to pursue that direction.
Yeah, thank you. I'm done.
Please, the next question from Professor Zvягin.
Thank you very much. Thank you very much for your interesting talk, and my questions are very simple and clarifying. First of all, I would like to understand. You speak about some, for instance, for some iron yttrium garnet, but it is, as far as I understand, it is the magnetically ordered system. As far as I remember, it has 64 magnetic sublattices, as far as I remember from 80s. And if you are speaking about the magnetically ordered system, how do you speak about the quantum effects? So magnons are just the small deviations of the magnetic vector from some equilibrium direction. That's all.
Right.
And you can forget about quantum effects at all.
Right.
This is
at some level. Sure. Okay. So one example. True. I mean, the theory to understand the yttrium iron garnet, you could fully understand it semi-classically, right? So it's just an ordered magnet with magnons. Yeah. But same in quantum optics. You could say, well, it's a classical Maxwell equations, but that's what is used in quantum optics. I mean, the photons are the quantum degrees of freedom that you utilize. Same here. So it's you can start with a classical theory, whatever, but the magnons are quantum objects. The quantum objects, so if you put NVs next to an ordered ferromagnet, the kind of quantum magnonics at the most boring level, it could mimic quantum optics. So those magnons simply replace photons. For example, as you could have spontaneous
magnons are bosons.
Yeah. So you put a single NV next to a magnetic material, it spontaneously emits a magnon, just like an atom can spontaneously emit a photon, and that is already a quantum mechanical process. So the underlying theory is semi-classical, but once you quantize it, that single magnon emission is fundamentally a quantum process. That's kind of the first issue to realize. You may not appreciate it, but the moment you put two NVs together on some length scales, remember I said like some coherence lengths. In this case, that coherence length will simply correspond to the wavelength of magnon, of the resonant magnon that you emit. So if you put the NVs close on the length scale of that magnon wavelength, now, and then you initialize them in some twisted state. Now the dynamics of those two NVs becomes intertwined with a spontaneous emission of magnon. So one NV can emit that magnon, the other NV can pick it up, and the dynamics becomes already correlated. And that's when you get the transient entanglement that I discussed. So it's really incredibly simple starting point that is already giving you some quantum dynamics. And like you said, the ingredients are very conventional. It's just an ordinary ferromagnet, which you could describe by LLG equation, but then we have to quantize. To quantize it, is already a good starting point. So it's not so much that you need to get some kind of exotic spin liquid or anything. it's more about the length scales and the spectral properties. You know, so the NV energy has to be larger than the gap, so you can resonantly excite the basically magnons available at the spectral region that you're interested in, and then the issue of length scales. You know, the placing NV is close enough on the wavelengths. So it's kind of becomes a little bit of engineering, and you just look for some compatibilities between them. But
thank you very much.
I think are compatible. So that, because the gap, the Magnon gap, like in YIG, is a few gigahertz depending on the details. And that's all the energy scale. That's why I kind of focused on magnetic systems, because the energy scales are naturally compatible with NV splitting.
Actually, the next my question is also clarifying. You're speaking about magnons, etc. So gigahertz. For gigahertz, the wavelength is about meters. So if you're speaking about inhomogeneities in your system, so
you mean meters? You mean for like optics?
Meters, of course.
Yeah.
Gigahertz is 1 meter. The length.
In optics.
No, it's not optics. Of course, it's even not microwave. It's gigahertz. It's not very not.
No, but in YIG, again, depending.
You're speaking even if you're speaking about terahertz, it's about millimeters. For optics, forget about optics. So definitely the length scale there. It's very large, much compared to the
not
scale
meters.
of the
sample.
No. Meters.
No, it's submicron.
That's a meters.
No, look, the exchange length in
you spoke about gigahertz.
The length scale, the characteristic length scale, is the exchange length it's like tens of nanometers or so, 100 nanometers, sub 100 nanometers.
1 gigahertz, it's 1 meter.
I don't know how you're doing this conversion. I mean, it's at the bottom of the spectrum, the length scale is infinite. But if you go, let's say if you go to twice the gap. So let's say the gap in YIG, just the natural gap, like whatever, due to shape anisotropy, I don't know, like it's gigahertz. It's in the range of a few gigahertz. Let's go to twice the gap.
Please.
Then the length scale is going to be of the order of exchange length.
By the velocity of light, so that's it. No problem. Okay, and the last question.
But it's not the velocity of light; it's velocity of magnons, which is relevant here. It's not the velocity; it's also like the whole dispersion. It's the exchange length.
No, you're speaking about the external sources, so it's light. I don't know.
You're talking about length scale of light.
Electromagnetic field. It's an electromagnetic field.
For us, this is all
not magnons for your system. So okay.
So for us, the relevant question. No, but hold on. The microwaves, if you drive your system with if you drive your environment here, the magnons with microwaves. Those microwaves are infinite.
Yeah, so in resonance, it's microwaves. So microwaves. You understand? But it's definitely not optics. Optics is much higher. The energy is much higher.
Optics, true. And
so nanometers. 100 nanometers.
It's all relevant. You use optics here to drive.
It is even not infrared.
To drive optic transition. So you use a green laser to drive NV dynamics, to initialize and to detect NV state. So that's the diffraction limit there is submicron. Then you don't have to use microwaves to drive YIG. In fact, we prefer to use electronic means to shape the environment. But in the first experiment that you mentioned, in one of the parts of that experiment, it was a microwave. Like you said, it's uniform microwave drive that drove Kittel mode, just a uniform mode. But NV centers do not couple with Kittel mode. So that Kittel mode would then evaporate into incoherent magnons. And those have length scale that is submicron. NV couples to magnons with submicron. wavelengths, which is unfortunate. I wish it was a meter. You know, if NV was coupling to magnons with that strongly, with that length scale, that means we could have a meter-sized device and all of the NVs would undergo correlated dynamics, which unfortunately we don't have. So that would be actually good news. Unfortunately, that's not the case. So, right, so anyways, the bottom line, the relevant length scale, the most relevant length scale here is the wavelength of magnons, and that's submicron, unfortunately.
Okay, thank you.
Thank you. And the last question, you spoke about the inverse, about negative temperatures. So that's that means that you have the just inverse population. That's all.
Yeah.
Do I understand you correctly? So
yes,
you are
yes.
speaking about the inverse population due to some external process, etc., etc., etc. So you introduce some inverse population which is related to some local inverse. Sure.
Local. Yeah. I mean, first of all, the temperature is very low. That means you could initialize, like out in a two-level system.
It's not the temperature in the thermodynamic sense. It's just some characteristic of your local multi-level system where you introduce, for instance, for lasing or for something else, you introduce the inverse population.
But it is a thermodynamic sense. It's the temperature of the noise that that is emitted, which looks So then, if it was a single spin, look at the level of single spin, everything is trivial, right? The point is, once you have more than one spin, and now you have this ability to one spin create inverted population, another spin not. You know, the combined dynamic becomes quantum mechanical. That's kind of the point.
Thank you very much.
Yeah.
Thank you.
Thank you.
But the ability to create inverted state at the level of a quantum impurity by itself is conceptually is nothing interesting, but the technological practical ability to do that would be spectacular. Basically, it would open up all of these games that we want to play. I mean, we're not that ambitious. Like we'll simply say, well, let's just cool it down a little bit. I mean, you know, I'm not even asking for the inversion. But in the Hawking radiation story, that's kind of what happens. On one side, you know, because the inverted magnet tries to also invert the qubit. And then Hawking radiation scrambles these dynamics on top of the inverted sort of twisted state. That's how you get maximally entangled state in the steady state. So, anyways, it's really this kind of rudimentary, simple ingredients which, when put together, make an interesting story.
Thank you. And we have time only for a short question from Alexander Porosenko, if possible. So we have some time constraints.
Thank you very much. In fact, I have a small comment or add-on. As far as I understand, you need at least a pair of strongly coupled two-level systems. I remembered that Alexander Burin from Tulane studied this model about 20 years ago to account for some low temperature phenomena in silica glasses. And yes, he considered a pair of two-level system with dipole interaction and different relaxation phenomena, interaction with microwaves, and so on at lower than 1 Kelvin. And in his picture, when you have a pair of identical two-level systems, if they exchange a virtual phonon, in fact, the Bell state is realized. So you have a flip-flop transition.
Absolutely. No.
If you can see his papers, Alexander Burin from Tulane.
No. You know, if you could realize very strong coherent interaction, you know, this virtual magnon exchange that just leads to coherent interaction, sure, you get strongly. That's basically a 2-qubit gate in the language of quantum computing. If that is stronger than the coherence, that's all you need, you know, to do quantum computing or whatnot. Our starting point here is opposite. Imagine you're in a situation that you do not have strong coherent interaction. So it's kind of pessimistic. We're starting with a pessimistic scenario. that you are dominated by not virtual, but like real magnon exchange. And it's kind of sort of complicated magnons have been emitted, absorbed. It seems like a messy situation that by conventional wisdom, you want to avoid. Instead, we show that even in this pessimistic scenario, interesting things happen. And moreover, when interesting things happen, it looks even better than the coherent state, because somehow the steady state is unambiguous. For the coherent dynamics, it's like you have to initialize and you have to time everything perfectly. Here we don't have to time anything. Eventually, when things work, in some sense, you imprint quantum dynamics, and then automatically you perform error correction. So you don't have to design error correction. Like the system just naturally evolves into some twisted quantum states. So then it seems even better in a sense, potentially. But thank you for the comment. I was not, somehow didn't emphasize it, but we're coming from a different angle.
And maybe you can consider color center in quartz also realized by substitution of aluminum, for example, or iron. Substitute silicon for aluminum or iron or some three-valent element, and then you'll realize a two-level system by capturing a hole. So
for me as a theorist, this that's why in the title I just say color center. The NV is just a placeholder. Any color center would work as long as somehow the aspects. Some of the basic aspects that NVs have, they also have in terms of good. Basically, you just need good enough decoherence properties and the ability to measure them. That's practical. There are practical issues that as long as they're good color centers for whatever the color centers are doing, I don't care. Another very attractive candidate are boron vacancies in hexagonal boron nitride. So that's kind of a new trend. Those they may not be as good. NV color centers are somehow spectacular, like in terms of like how they don't bleach, like all these kind of practical issues that as a theorist I don't want to worry about. Like experimentalists tell me, well, don't worry about those for the NVs, but for the other color centers, you might have to worry about all sorts of issues. Any color center will work for this purpose as long as the key goal is that they're good color centers and you could compactify them. They remain to be good color centers, even when you have, let's say, tens of nanometer spacing between them, very, very, very high density. And if you can plan them in films, that's even better. So and these are not as good with that. Boron vacancy in HBM seem very interesting. And boron vacancies in HBM, they're already present or placeable in kind of van der Waals heterostructures of much interest for the kind of things we're after.
Okay,
thank you. Thank you, Yaroslav, for wonderful question and answers session, and thank you for a great talk. So I see that maybe we could ask more questions. So I advertise. So I suggest to everyone who would like to ask more questions to contact directly Yaroslav. I think he will be happy then to answer. So So then with this, we would like to finish our seminar today, and we are looking forward to seeing you again, and in Kharkiv in particular in near future.
Looking forward.
Thank you.
Thank you, guys. Bye-bye.
Thanks. Bye-bye.
Bye-bye.
Thank you.
Bye-bye.
Thank you.